Okay, so this is semiconductors, and as you can see, question 1, you have a couple of diodes, one going one way, one going the other way. We know diodes allow current in one direction only, so you can see that the current will be going round. Current will be going around this way, like that. So obviously L1 will be on, L2 will be on, and L3 will be off, because you can see that the current will not go through that one. Okay, the circuit diagram shows a 6-volt battery connected to a diode and a lamp. Complete the table by adding the readings on the voltmeters. Okay, so V1, remember voltage is potential difference. So the potential difference of V1 would still be 6 volts. All of the voltage is dropped across that component there. Okay, so then what do we need for the second one and the third one? Well, I know that a diode, if it is conducting, it's 0.7 volts. The potential difference is 0.7. So I know that that is 0.7 volts. And as we know, the volt drops around the circuit. Therefore, V2 will be the remainder, which I know, do that in my head, 5.3 volts. Okay, so we need to protect this transistor, and what happens is when a motor or anything with a coil of wire, you get a magnetic field, electromagnetic field, and when you collapse that field, break the current or break the circuit, the current wants to go back up the other way. So we need a component to protect. Okay, so obviously a diode there, like so, will allow the current to flow back up the reverse direction. It's called back EMF, electromotive force, but that's a phenomenon, what it's called. Okay, so for this one, let's read what it says. Blue LED indicates when the output of a logic system is 1. When lit, the LED passes a current of 25 milliamps and has a forward volt drop of 3.2 volts. Okay, so when a logic 1 is there, we have 10.2 volts. Okay, so first of all, calculate the power dissipated in the LED when it is lit. Well, if we know the current going through the LED, don't we? And we also know the volt drop. So we know that power equals V times I. We should be able to work that out. The second part, it says the minimum resistance of resistor R, which limits the current through the LED to 25 milliamps. Sorry. So this time we're going to use Ohm's law for this. And then we need to work up the minimum power rating for the R value. So I've got the solutions here and I'll just talk through them. Okay, so just part I, and II. Let me just get the laser pointer actually. Okay, so you can see then that the power dissipated, we've just used V times I. So the voltage multiplied by the current, it's 25 milliamps multiplied by 3.2 volts, 80 milliwatts. Remember, if you're using just 25, the answer will come out in milli because you've got milliamps. Okay, you could put 25 times 10 to the minus 3 and it will come out in watts, which is 0.08 watts. That's fine. Okay, so the minimum resistance to limit the current to 25 milliamps, so Ohm's law then. So if we know the voltage across there is going to be your 10.2 minus your 3.2. Okay, so and then that's this bit here. Okay, and then obviously we know R is V over I, so that voltage divided by the current gives me 0.28 kiloohms or 280 ohms. Okay, and then the power rating, power is V times I. So if we know the voltage is 7 volts and we know the current is 25 milliamps, it will come out in milliwatts. Okay. Okay, so for this one, part of the same question, E24 series, we need to find the resistance value. So this is from the previous page, but the resistance value, the nearest one, you've got the option of 270 or 300. Now you want to limit the current to 25 milliamps, so obviously the higher value you would choose, that's to be 300 ohms. Yeah. And then the suitable power rating, you need one greater than 0.175 watts. So obviously the next nearest one will be quarter watt, 0.25 watts. Okay. This exercise here hopefully is straightforward. You've been given the current gain, you know the base current, and you need to find a collector, or vice versa. Essentially, in my head, the way I always do this, let me get my pen out in fact. Let's just get the pen. Okay. So we know that HFE equals IC over IB. Yeah. In other words, the input, which is the base, multiplied by the gain equals the output, doesn't it? So 4 times 50. Yeah. So that's your first one there. Your next one, you've been given the output current, so the input has to be smaller. In fact, it's 120th, so 60 over 120 is 0.5, isn't it? We're milliamps and milliamps there. Okay, and then your last one, it is this equation, that's divided by that 150. Okay. Okay, so next question. So this time we've been given a transistor and we've been given a current gain of 120. We've been given V in is 1.8, which just saturates the transistor. Okay, so if it's just saturated, it means that obviously all the current is going to be going down there. IC is going to be going down there. We need to work out that current. So the way to work out that current, they've given you a lot of information. It's just Ohm's law, really. So if you know that you've got a 150 ohm resistor there, we know there's 9 volts there. So if it's just saturated, all of the voltage will be across that resistor there. There will be 9 volts across that resistor there. So I equals V over R. Okay, so we'll show you the solutions in a moment. The base current, again like the previous question, if I know that the gain is 120, how many times bigger or smaller will the input current be? 120 times smaller, yes. And then the volt drop across the resistor RB. Let me just press enter there. The volt drop across the resistor RB. To turn a transistor on, we always need 0.7 volts. Yeah, so between the base and the emitter, you always need 0.7 volts. So if V in is 1.8 volts, I know I need 0.7, so the rest of the voltage will be across for RB. Okay, so you can see for part III, the volt drop is 1.1. Then we can work out the resistor value, because as I said before, we know the base. I told you about the calculation to do that. It's 0.5 milliamps. I know that the volt drop is that, so we can use Ohm's law. You see, it's all about Ohm's law mainly. R is V over I, so we can work out that one there. Okay, with this one, use a graph to determine V out when V in is 1.3. Just so you know, this graph, the examiner likes these. So this is where the transistor is off, because all the voltage is across it. V out, you have 9 volts. If you've got 9 volts across it, it will be off, because obviously there'll be 0 volts there, won't there? So that's when the transistor is off. When a transistor is on or saturated, there is 0 volts across it. So if there's 0 volts there, there would be 9 volts there. That makes sense, doesn't it? It's saturated. You've got this middle bit, this gradient where it's neither on or off. We call it the active region. But anyway, what it's saying is use the graph to determine V out when V in is 1.3 volts. Well, 1.3 volts, let's just dot up. That's probably too high actually. That's 1.5, that's 1.25, maybe about 5-ish, volts, something like that. I think the mark scheme's done it slightly differently to that. But anyway, yeah, maybe about 5-ish volts, I think. Anyway, and then calculates the value of the collector current and the power dissipated in the transistor when Vin is 1.3 volts. So obviously it depends on what value you've chosen here. Let's see what the examiner has chosen. We'll go with what they've chosen. Yeah, they've chosen 6 volts. I'm not convinced that's 6 volts, to be honest. Maybe, I don't know. But anyway, they've chosen 6 volts. So if we go with 6 volts, okay, let's just get rid of these bits here. I'll show you how you can do this as a calculation. So it's saying that V out is 6, so therefore the voltage across there has to be 3 volts, yeah? So therefore we can work out the collector current. So if I know there's 3 volts there, and I know it's 150 ohms, this is this calculation there, 3 volts divided by 150 ohms gives me 20 milliamps, okay? So that's my collector current. And then calculate the power dissipated in the transistor. So if I know that there is 6 volts across the transistor, and I know the current going through the transistor is 20 milliamps, then I can use power is V times I. So it's your 20 milliamps multiplied by your 6 volts, yeah? Okay, which is 0.12 watts. So it's just using, again, Ohm's law and your power equation, power is V times I. Okay, but I'm not convinced the examiner or whoever did this has actually got that right as 6 volts, but there you go. Okay, next question. We have a temperature sensing circuit. This is called a thermistor. So switches on a warning lamp when the temperature rises above a certain threshold. Okay. So basically, just so you know this, as the temperature goes up on a thermistor, as the temperature increases, the resistance always goes down. If the resistance is decreasing, then the voltage is also going down. If the voltage is going down on this top bit, it's the same as me saying the voltage is going up on that bottom bit. I hope that makes sense, because it's a potential divider. Okay, so it's asking quite a few things here, but it's actually quite straightforward. So just using the same ideas. Okay, so let's have a read. So the transistor has a current gain of 850. Yeah. During testing, the base current was 0.8 milliamps. So we know the base current when the temperature was sat just above the threshold. Okay. However, the lamp, though lit, was dim. For a base current of 0.8 milliamps, calculate the value of the collector current. Okay, so we need to find the value of that collector current. Okay, and we've been given, obviously, the base current of 0.8 milliamps. So how would I find that collector current if I knew the input current and I knew the HFE? Okay, yep, correct. So you'd use that HFE equation. Okay, I'll just put the answers on for this now to show you the rest from here. So the collector current is HFE. If I let me get my pointer now. So you can see that the IC is HFE times IB, or input current times gain equals output. So we know that one. Next question, the volt drop across the lamp, which has a resistance of 10 ohms. So if I know the resistance of that, and I know the current going through it, surely I can find the volt drop across it. Yeah. So we know the current, we know the voltage, V equals I times R, it's Ohm's law. Okay. You can see it's all coming back, it's just Ohm's law. Okay. Next, the voltage V in. Okay. So the voltage at that point there, we need to work out, where are we, the voltage across the base resistor first. So if I know that the base resistor is 4.7K, and I know the current going through it, I can work out I have 3.76 volts at that point there across that resistor. Remember to add on the magic number of 0.7. Students always forget that. So make sure there's always 0.7 volts across there. So 0.7 volts plus this voltage equals V in, which is this voltage there. Okay, so it's 4.46 volts. Then we can work out the current going through that 1K resistor, can't we? So if we know the voltage, we know it's 1K, quite simply, it's 4.46 over your 1, 4.46 milliamps. Okay. Then we can work out the resistance of the thermistor. It does say there to remember to include the base current in this calculation, because if you think about it, the current splits at this junction. So you know you've got 0.8 this way, milliamps that is. We know we've got 4.46 milliamps this way. So basically the current going through there is 5.26 milliamps. You can see that. So it's just addition, just add them together. We know the voltage there would be your 12 volts minus your voltage there, which is 7.54 volts in total. So then we can use Ohm's law as usual. R equals V over I. So you can see it's that one there. So the thing that students would probably forget there would be maybe to add that 0.8 in for the current. Okay, so if it's telling you there to include that base current in that calculation. Okay, for this last bit, it's saying why is the lamp only dim in these conditions? Well, obviously you haven't got all the current going, all the collector currents needed for that for the 10 ohm resistor. 10 ohm bulb, have you? Ideally, you want 12 volts across there. So because you haven't got that, then obviously it's going to be dim. Essentially, the reason is you haven't got enough base current. Why haven't you got enough base current? Well, essentially, the thermistor resistance is too high. So it's all kind of linked, isn't it? So this is kind of what's going on here. So to fully light the lamp, as I've just said, you need 1.2 amps because you need 12 volts divided by your 10 ohms. We need 1.2 amps. Okay. This would therefore mean that the base current needed would be 1.2 milliamps. I've basically taken 850th of that value. Okay. We haven't got 1.2 milliamps available due to that the thermistor resistance being too high. Now this comes in a lot. Rule of 10. Okay. Well, rule of thumb, rule of 10. Essentially, when you have a potential divider, you want the current in the potential divider to be 10 times higher than the output current available as a rule of thumb. So that means that the current going through the thermistor should be at least 10 times higher than that, about 12 milliamps. It isn't that. In fact, it's about 5 milliamps. Therefore, it won't be fully lit. Okay, so if this thermistor had a lot lower resistance, there will be more current flowing there, which means the base would be higher, which means obviously the lamp would be fully on. So it's again, rule of 10, generally speaking, as long as it's about 10 times greater current, or you can say it the other way around, the output current will be about a tenth of the current going through the potential divider. Okay, so this is a question regarding Thevenin's theorem. This comes up all the time in various different questions, but it's relatively straightforward. Thevenin's theorem, you just need to know how to do it. But that's a potential divider. Now, when I talk about potential dividers, I always, the analogy I always try and use is if you're thinking about apples in a basket. So I've got 2 apples in a basket and a further 3 apples on the table next to the basket. And I have to say what would be the ratio of apples in the basket. So if I don't say that, a lot of students say there'll be 2/3. There won't, will there? There'll be 2/5. Yeah? So it's 2 over the total, isn't it? Okay? So let's go back to this question then. First of all, we want to find VOC. So VOC will be 2/5 of 15 volts by ratio. So I'll put the answers on in a moment. Once you've done that, do you remember we have to find the short circuit current, we have to short out the bottom resistor. So if that bottom resistor isn't there, then the current would come this way because it's been short circuited. If that was a wire going down there, it would just be going that way. So it'll ignore this 2K resistor. So if I was to find the current, the short circuit current, it will be your 15 volts divided by your 3 kiloohms. So your short circuit current will be your 15 volts divided by your 3 kiloohms. Remember, if you're using kiloohms, it will just come out in milliamps. Okay. So that is that one. And then the equivalent resistance is quite simply R equals V over I. So it's VOC over ISC. Open circuit voltage over short circuit current, 1.2 kiloohms. Okay. So we've worked that out now. Now, then it just becomes really, really easy. It's just series circuit rules now. So use the equivalent circuit to determine the base current IB. That's that current going down there. That will produce an input voltage of 4 volts. Well, if there's 4 volts there, I know that VOC is, or was, 6 volts. So surely, if I've got 6 volts there, 4 volts there, what voltage will be across that equivalent resistance? Of course it's going to be 2 volts, isn't it? There's 2 volts across it, and I know the value of the equivalent resistance. Look, we calculated it's 1.2 kiloohms. Surely I can find the current IB in that situation. It's quite simply Ohm's law. It's 2 volts divided by your 1.2 kiloohms, so it'll be 1.67 milliamps. So don't be scared with these sorts of questions. They're dead easy. It's a potential divider. Think about the Apple scenario. You can't get that wrong. And then it's just Ohm's law, series circuit rules of Ohm's law. Okay. So again, another potential divider here. Light sensing system. LDR has a resistance of 2.4K and light level 900 lux. Okay. Use a voltage divider, rule of thumb, that's the rule of 10, isn't it, to estimate the maximum current that can be provided. So essentially, we're going to work it out. We're going to work out the current in this situation. So if I know the total resistance is 6K, isn't it? So 6K in total is 12 volts. So it's going to be 12. I equals V over I, doesn't it? 12 divided by your 6. Okay. And then obviously that's going to be the current there. But then you have to remember that only 1/10 of the current is going to be available to come out. Okay. So you can see that we have obviously your 2 milliamps, your 12 over your 6, 2 milliamps there. But then using the rule of 10, only 1/10 of that current will be available. So it's only 0.2 milliamps available. Okay. So that's what that's asking there. Then we can just do your bog standard VOC and ISC to find the equivalent. So we know how to do that now. There's 3.6 lots of the total resistance. 3.66 of 12. 3.66 of 12, 7.2 volts. Short circuit, short out bottom resistor, so it's going to be 12 over 2.4, 5 milliamps, and then work out your equivalent resistance by doing VOC over ISC. Okay, so there we go. In fact, it's sketched over here, so you can see there's my sketch. Okay, then it says the light sensing system is connected to a transistor switch. Okay, that's fine. Use your equivalent circuit to calculate the input voltage when the base current is equal to the answer in part A above. So what was part A above? It was 0.2 milliamps, wasn't it? Okay. So if I've got 0.2 milliamps available, I can work out the volt drop across the equivalent resistance first of all. So for now the equivalent resistance is 1.44 kiloohms. then I can basically do V equals I times R. So you can see here, I know that the volt drop is 0.288. The input voltage to the transistor would be 7.2. Sorry, there's 7.2. So minus the volt drop across there gives me 6.91 or 6.912 volts. Okay, so that would be how I would work out the input voltage there. Okay, so it's just the difference in voltage there. 7.2 minus your volt drop. Okay. As a percentage, it would obviously be 0.288 over your 7.2 times 100, so it's 4%, which is good because we said about it being 10% or less. So it would be absolutely fine using the rule of 10. Okay, so that's the idea of that one there. Okay, on to a couple of MOSFET questions. Metal oxide semiconductor field effect transistor. Yes, I know that's sad. Okay, this one we just need to add the switching device, which is obviously the MOSFET itself. So just need to remember how to draw one of these. So they go like that, like that, like that, like that. And next year you'll actually learn what's inside of them. Okay, that goes up to there, and that goes down to there. And a component to protect from back EMF. Do you remember the very first question? Back EMF. Because it's a solenoid, so it's a coil of wire. So electromagnet, you get current wants to go back up the other way. So stick a diode there, and it will protect that component. Okay. This next one, we have a MOSFET, fan motor. Okay, that's lovely. The MOSFET has a transconductance of 3 Siemens and an on resistance of RDS means drain source. Just so you know, current goes down the drain, out of the source, and the gate turns the thing on. And the current is going down that way. I'll do current there, sorry. Current's going down. So down the drain, out of the source. Okay, so there's a couple of equations on the data sheet that you can use. So just look at the data sheets, it's all on there. So on the data sheet, you get the drain current. Let's go to my highlighter now. So you get the drain current equals the transconductance VGS minus 3. That's on the data sheet. So this time we've been given drain current of 2, we've been given GM of 3. Rearrange that equation to make it the subject. I hope you're okay at rearranging these equations. Basically divide both sides by 3 and then minus 3 off both sides, or plus 3, sorry, to both sides. Okay, if you need some work rearranging these equations, just plug them in to start with and see what you get. Yeah. Okay, and power dissipated, this is also on the data sheet, I squared R. So if we know the drain current is 2 squared times your resistance between the drain and the source when it's on. Well, that's given in the question. Okay, we're essentially using the same equation. The light sensing unit produces an output voltage of 6.7. The MOSFET has a transconductance of 2.3. This time we're working out ID. So it's the same equation, really. There you go. So VGS is 6.7, GM is 2.3. Rearrange the equation. What you guys might want to do is try and select it and do it yourself. Yeah. Okay, so sometimes the advantage of a MOSFET over a transistor, you require a base current, and then it gives you an amplification, the HFE, then it gives you a larger output current. The advantage of a MOSFET is you don't need any input current. You need an input voltage, then it gives you a larger output current. So the input current is 0 amps. Okay. Then these two are just straightforward. It's just using the same equations, isn't it? Really easy. Why don't you have a go? Why don't you pause me and look at the equation on the data sheet and just plug the numbers in? Yeah, for GM, which is the transconductance, obviously we're going to need to know the drain current, which is there. We've been given the drain current, and we need to know Vn, which is given there. So it's just those two values is what you're going to need. RDS on, we're going to need, it's Ohm's law, R is V over I. So what voltage are you going to need for that? That voltage there. V out is given in the question. What current are you going to need? The current going down there is given in the question. Yeah? And then obviously the power dissipated, power in the MOSFET. So that's, you can use RDS on for that. That's the I squared R1. Again, it's on the data sheet. Okay, so as you can see, this one here, plug the numbers in. RDS on, plug the numbers in, and then obviously that one there. So try that one out yourself.